I'd like to welcome you all to the Energy Policy Seminar. This is a weekly event that is co-sponsored by the Belfer Center for Science and International Affairs, the Mossavar Rahmani Center for Business and Government, and the Salada Institute. It is being recorded simultaneously, or it's virtual simultaneously. So thank you all for coming. Today's talk is entitled Breaking the Cost Escalation Curse on Nuclear Power. Our speaker is Shangwei Liu. He is a postdoctoral research fellow at the Belfer Center. And his research focuses on accelerating clean energy innovation and deployment to minimize greenhouse gas emissions and costs while maximizing co-benefits and equity. He has worked on nuclear power, green hydrogen, and solar energy. He holds a doctorate in science, technology, and environmental policy from Princeton University's School of Public and International Affairs. He also co-hosts a Chinese podcast about climate science and policy. So we're very privileged that he is with us today. Let me turn it over to Shangwei.
Thanks, Henry, for the introduction, and thanks everyone for coming. Today, my talk is basically about nuclear power, and especially focus on the economics of nuclear power in China. And this work is collaborated with Professor Minghao Qiu at Stony Brook University and Professor Gang He at the City University of New York. Before I jump into the nuclear power, I want to give people a brief introduction of my research so people can understand what motivated me to do a nuclear power projects. As Henry said, I'm postdoctoral fellow here, and I graduated from Princeton's Public Policy School. And my research is basically focused on everything about energy technology, its innovation, its deployment, and its policy. Most of the time, I'm a modeling person. I do a lot of system modeling, like integrated system models, power system models, building energy models. And sometimes I also do research, like focus on empirical study, either using colorimetrics or do statistical analysis. And today's work is more like a simple empirical analysis and focus on the energy innovation. I think the overarching question for the energy innovation is basically to understand why some energy technologies fail and others succeed. And from my perspective, people usually talk about this question from three dimensions or three key factors here. The first factor is the nature of the technology, like the inherent characteristic of different technology. If people say, like you say the development of solar and nuclear power, they are different, people will say the two technologies are different, right? Nuclear power is large scale, it's risky, it's complicated. And solar panel is very different. Solar panel is simple, it's a granular technology, it's easy to produce. That's the first factor. But people can also say, like, even for the same technology, what we observe is like sometimes one technology works in one country but doesn't work in another country. So this comes to the innovation system. Different institutions, different culture, different supply chain, different financing situation, different infrastructure. One example I give here is the railway system in United States versus China, right? People will say, like, why this? You can see the difference is like the different population density, different resources, different infrastructure. And the third one is public policy. And policy also matters. It depends on like what regulations you can give to people or like what incentives you can give to people. One example I give here is like if people think about the development of solar panels, we have to go back to the 2000s and think about one policy, which is really important for solar panels development, that Germany's feed-in tariff policy, introduced in, I think, the 2000s from their Renewable Act. Basically, you give the solar developers guaranteed revenue. When people think about the whole energy innovation, usually people are talking about the interactions between these three key factors. And what I'm going to do today is really simple, is to tell people a story on nuclear power. So I'm not an expert on nuclear power, but rather I'm talking about this problem from the energy innovation perspective. And speaking of nuclear power, here is just a lot of highlights showing people this is a hot topic. There is growing interest in nuclear power from the traditional nuclear players. Nuclear power, I think, is one of the few bipartisan, one of the few things get bipartisan support in the United States, and a lot of new legislation, new policies coming out. In France, the government want to build six more new nuclear power plants. And you can see the same thing in Japan, in South Korea. A lot of traditional players, they are thinking nuclear power resurgence. And on the other hand, you see a lot of emerging countries, they are either building their first nuclear power plants or consider building their first nuclear power plants. And also besides the public sector, you see a lot of interest from the private sector, especially driven by the demand from AI and also the data centers. Like the Microsoft is seeking to reopen the 3 Mile Island power plants to power their data center. And Amazon, Google, they are investing in the small module reactor to power their data center. But anyway, I'm trying to say this is a hot topic, and there is growing interest in nuclear power. But on the other hand, nuclear power is always a debatable issue. A lot of things we can debate, right? We can debate on its safety. Do we want like another nuclear accident, a disaster? And other people can argue that the nuclear accident, that risk is actually pretty low and it's declining because the technology is improving. And what's the role of nuclear power in grid decarbonization? Some people will argue that nuclear power is cheap, it's a firm resource, it's reliable. But other people can say we can totally do decarbonization without nuclear power. And also its cost and its construction time. Some people will argue that it's really expensive to build nuclear power plants in United States today. But other people will say, if you have the regulatory stability, if you can do standardization, you can make it cheaper and build that faster. And also on nuclear waste, we still don't have any permanent solution on nuclear waste. But people can argue that this is totally manageable and you only have the relatively small amount of waste. A lot of things we can debate, but today I'm really going to focus on the economics of nuclear power. The reason is like, I think people have a consensus is like, what's the fundamental barrier for nuclear power today is its cost. It's too expensive. I have a quote here that's from the MIT's The Future of Energy Studies. Like their conclusion is the fundamental problem of nuclear power today is their cost. So my talk today is really going to focus on the cost of nuclear power. Speaking of the cost of nuclear power, it's a form of electricity. And when we talking about electricity's cost, we usually use the LCOE, the levelized cost of electricity, to represent its cost. What I'm showing here is a classic equation to calculate the levelized cost. Basically, you have the capital recovery factor and construction cost, operational cost, maintenance cost, fuel cost, and divided all costs by the electricity produced. And think about the nuclear power. For nuclear power, its operational cost, maintenance cost, fuel cost are relatively stable. And also electricity production are also pretty stable because they usually use as a base load with high capacity factor. So what really matters in this equation here is the construction cost. And the construction cost can be divided into two parts. The first part is basically everything except the financing cost. People call that overnight construction cost. And the second part is the financing cost, the interest during construction, which depends on your construction time and interest rate. So today my talk will basically focus on the overnight construction cost. And I will also discuss something on the construction time. The reason why construction cost is a problem is because historically we have observed an interesting and concerning fact. is people call that the cost escalation curves of nuclear power. If you think about that, like a lot of technology, like solar, wind, batteries, electric vehicles, when you produce more, when you build more, you can produce cheaper, you can build cheaper. But nuclear technology is very different. Historically, when you build more nuclear power plants, you build it more expensive. What I'm showing here is the overnight construction cost of nuclear power in the United States. And you can see the cost increased dramatically over time. This one, that's a Vogtle. That's the 2 nuclear power plants commissioned last year in the United States. It's very expensive. It's about $15 per watt. One thing I want people to notice here, the cost increase happened before the 3 Mile Island effect, the 3 Mile Island accident, and it increased dramatically after the 3 Mile Island accident. The reasons for this cost escalation curves in the United States, the first is like, it's very interesting because that's a fragmented market. So every nuclear power plants in the United States are built differently. So basically a lack of standardization. And the second thing is the labor cost and the material cost was increasing over time. The labor productivity is decreasing over time. And for the material part, it's like people know that if you build a nuclear power plants, you need a lot of steel, a lot of cement. And in many cases, you need the special steel and special cement for nuclear power. And that special like steel, cement, concrete is getting more and more expensive over time. Another thing in United States is the regulation stuff. Especially after the 3 Mile Island accident, the regulation get more and more stringent and keeping changing over time. So you can imagine if you want to build a nuclear power plants and the regulation is changing. So in many cases, you have to remove your previous work and redo the work to meet the new standard. And it can be really difficult, and that increases the cost. The cost escalation curves is more like a global phenomenon. It's not only United States, but also happening in France. What I'm showing here is France, the overnight construction cost in France. And one thing is very different is like in France, they have a centralized regulatory regime for nuclear power and really try hard to do the standardization. And you can say they choose different models from the CPO, CP1, CP2, P4, revised P4, N4, and recently the EPR model. And if you look at the figure, basically you can feel like the construction costs actually remain stable within within the same model design, but cost escalation curves happened when switching to a new model. That's the difference between what happened in the United States and what happened in France. And why they are switching to more expensive model? One thing is like nuclear power plants get larger and larger, and simultaneously get more and more complicated. The reason why it's got complicated, one reason is actually like the French company, they introduced the technology from the Westinghouse company, and that's the US technology. And they want to make it have some French style, so make it more innovative. And when you make it more innovative, you make it more complicated and increase your cost. So the problem here is like we have observed this cost escalation problem. And the debate here is like, is this problem a technology problem or this problem a policy or the innovation system problem? Remember the 3 factors here. I think this debate is really important because if this is an inherent nature of technology, like nuclear power is a bad technology, what we should do is to redesign the technology. And if this is more like a policy or innovation system, that's another direction. We should redesign the policy and innovation system. And when I like looking at this debate, what I'm thinking is like maybe the China's experience on nuclear power can contribute to this debate. The reason I think Chinese experience is valuable is not only because I'm Chinese, but also if you look at the recent development of the nuclear power expansion, the figure I'm showing here, the left one, that's the global operating capacity since 1970s. And you can see the largest country today is the United States, the second one is France, the third one is China. And most of countries actually stopped building nuclear power plants after 1990s. And China is the only country who has substantially expanded its nuclear power capacity over the past 2 decades. And the right figure here is that's a new capacity. And you can see China is constructing a lot of nuclear power plants, and a lot of nuclear power plants are in the pipeline. So what I'm thinking is like it will be pretty interesting to think about like what happened in China. Like is there any cost escalation curves in China there? What I did is really simple. I try my best to collect the construction cost of Chinese nuclear power. And let me just show people the results. The whole presentation will be basically focused on this figure. What I'm showing here is the overnight construction cost of the Chinese nuclear power plants. The circle, that's the operating units. Triangle, that's the units under construction. Before I go to any detail, let me tell people my data source and methodology. I would say that collecting cost data for nuclear power is challenging everywhere, and it's really impossible to get the third-party audited data. It's basically impossible everywhere. And people usually rely on the gray literature, like news report, to get the data. That's how people get the data from United States and France. And I do the same thing for China. The advantage is like I can read Chinese, so I can have a lot of sources. So basically, I use a lot of data from news, industrial reports, statistical yearbooks. I actually get a lot of data from the environmental impact assessment reports, because like when the nuclear power plants, before we start construction, before they start operation, they need to submit the environmental assessment report to the China's environmental department. And in their reports, usually have like the total investment for this project is a blah, blah billion. So I actually get a lot of data from there and also interviews. Let me give one example here. This one is the Taishan nuclear power plant. I think it's probably one of the largest nuclear power reactor in the world. And I get it from news to show that the Taishan nuclear power plant, their cost is 85 billion. So I know its capacity, I know that's the total investment. And what I'm doing here is like, first, I really try to use the final cost. You know, this is a nuclear power plants, and you definitely will have, in many cases, you have the cost overruns. In a few cases, I observe the cost underruns, but I really try to use the final cost in this figure. Like for this specific project, it was like the initial cost was like 50 billion. So that's huge cost overrun for this project. That's first thing, I use the final cost. And what I get here is the total investment cost. And I want to compare the overnight cost. So I basically convert the total investment cost to overnight cost based on their construction time and the interest of 3.5. The reason I use 3.5 is because Chinese nuclear power companies, they're usually state-owned company, and the interest rates they get from my data source is like 3 to 4%. So it's very low and pretty consistent. So that's how I convert it to overnight cost. And I adjust it to 2020 price based on the consumer price index and convert to US dollars. That's how I get this figure. And one thing I want to show here is like actually most of the nuclear power plants in China is built in twin. So you build two nuclear power units simultaneously, usually build one short after another. And they are roughly identical units. So I assume they have the same overnight cost. That's why you see a lot of double dots here. That's all double dots, double dots, double dots. And sometimes they build 4 units simultaneously. So you can say 4 units here. And in this case, that's 6 units simultaneously. So that's basically how I get the data in this figure. So next part, I want to give people a brief history of Chinese nuclear power industry. The Chinese nuclear power industry has a very short history, since 1980s to today, roughly 50 years. And I think the 50 years can be divided into 3 phases. The first phase is more like the early stage of Chinese nuclear power. Since 1980s, after the China's reform and opening up, the electricity demand is increasing. So people is looking at using more nuclear power. At that time, China introduced a lot of foreigner technology. So we collaborate with a French company, with a Canadian company, with Russian company, and introduce their technology. And simultaneously, China also developing its own domestic model, the CNP model and the CPR model, based on the French technology and also based on the previous nuclear marine experience. That's the first phase, and you can see the cost was decreasing over time very quick. The second phase is something more like the 2005 to the Fukushima accident in 2011. In this time, I think it's in 2005, the Chinese government announced a very ambitious plan to develop nuclear power. And they want to build a lot of nuclear power plants using domestic CNP and CPR model. And that's the phase 2 here. Most of these nuclear power plants, they started construction before the Fukushima and finished their construction after Fukushima. And you can see these domestic models, their costs are relatively low. And after Fukushima, the Chinese government thinks they need a safer and more efficient technology to avoid a Fukushima-like accident. So they want to introduce what we call the 3rd generation nuclear power technology. So all the previous model designs, they are 2nd generation, and China want to introduce a 3rd generation technology. So we collaborate with the French company to introduce the EPR model, collaborate with the US, the Westinghouse company to introduce AP1000 model, and also developing Chinese domestic 3rd generation model, the HPR model. And people usually call these units the first of the kind units or fork units, because that's the first time you build a model, you build a nuclear power plants, use this model design. So it's understandably, they have higher costs and longer construction time. These ones are all the fork units here. And I think after it's 2019, the Chinese government feel more confident in the 3rd generation technology, and they're starting to build more nuclear power plants. That's why you see a lot of nuclear power plants are constructing, they're under construction there. Okay, that's the history. From energy innovation perspective, what is striking to me or interesting to me is in general, you see the cost trend is decreasing. Overall, it's decreasing, and very different from what we observed in France and what we observe in United States. And how to explain this? I think in the next 20 minutes, what I want to persuade people is basically the key driver of this cost decrease is an indigenization process. Basically, because the Chinese equipment are cheaper and Chinese labor are cheaper. This a supply chain build up stuff. And a lot of conventional mechanism, people use that to explain the cost trend in solar, wind, batteries, doesn't work for nuclear power. Like the size, like the economic of scale, like learning by doing, like changing construction time, they don't really have any impact for the role in this cost decrease. So first, my key argument, indigenization drives the cost reduction in China. What I'm showing here is one evidence here. This is a figure showing the domestic content rate of nuclear power plants in China versus its overnight cost. And you can see that's a very strong linear relationship. the domestic content rate is basically reported by the nuclear power company, because that's one matrix, that's their achievements. So they will make that public. And they usually calculate that based on the contract value. You know that if you build a nuclear power plant, you sign a lot of contracts. Sometimes you give the contracts to the foreigner company, and other times you give them to the domestic company. And they basically calculate the domestic content rate based on the contract value. And if you read the Chinese nuclear power history, you can get a lot of stories, like when replacing foreigner equipment with Chinese equipment, it gets cheaper. When replacing foreigner labor with Chinese labor, it gets cheaper. So I would argue that what we observe here is basically an indigenization story, a supply chain story. That's my key argument here. And another thing I want to persuade people is like a lot of conventional mechanism, as I said, like we works for solar, wind, or like batteries, doesn't work for nuclear power. The first thing is the reactor size, or people that call that the economics of scale. Basically, there are two constructing arguments. One, people can say you have the economical scale, because if you build a larger nuclear power plants, you can increase the building efficiency, and you can spread your fixed costs over a larger capacity, so you can lower your cost. But on the other hand, you also have the diseconomy of scale. That's like when you build a larger nuclear power plants, it's also get more complicated, more complex. So you have the mega project syndrome, which increase your cost. Historically, what we observe in United States and in France is like the diseconomy of scale usually dominates the process. So it's more likely the current nuclear power plants are too large. I think this also motivated people to think about like the SMR, the small modular reactor, or smaller nuclear power plants. But anyway, in China, this doesn't really important, because what I'm showing here is like the relationship between size and overnight cost. In here, actually, a lot of nuclear power plants are overlapped here. Basically, in China, most of nuclear power plants are about 1 gigawatt, and reactor size doesn't really important here. That's the first part. The economic of scale doesn't really important in explaining the cost trend. The second part is like learning by doing, and I think that's hot word. And people talk about like how learning makes a solar chip, make battery chip, makes a wind chip. But I would argue that the learning effects for nuclear is very limited, and it's really like because of the inherent nature of this advanced nuclear power. And we basically, to explore the learning effect from 3 channels, I will discuss them one by one. Basically, learning means if you have cumulative experience, you have more experience, can you build nuclear power plants cheaper or faster? So let me first say about the first channel. The hypothesis is like here, like if you have learning, you have cumulative experience, probably you can make it cheaper when you build the nuclear power plants, have the similar reactor design. And if we go back to the figure, like most of the Chinese nuclear power plants actually using 2 models today, the CNP model and the CPR model. So my question is like, is there any learning in the CNP model or the CPR model? For the CNP model, my results is like the learning rate is not statistically significant. And the cost in, up and down here actually can be explained by the indigenization process pretty well. And for the CPR model, I think CPR model is like concentrated in the southern China and is more standardized. So we do observe some learning, but this learning is really like a mixed effects of learning by doing, of the indigenization process, and also the multi-unit siting stuff. And you can say the CPR model, at first that's 2 units simultaneously, and 4 units, and 6 units. And I think that also helps the cost reduction of the CPR model. But the reason we can only do that, this is also suggestive evidence. because we do not have any detailed data. So we think like maybe we do not look at the cost, but rather we can look at the construction time. Because for the construction time of nuclear power plants, the data are accurate and widely accessible. So our question here is like, if you have cumulative experience on building nuclear power plants, can you build it faster? Before I go to the results, I need to tell people how to build a nuclear power plants. That's some skill people can learn. So basically, if people want to build nuclear power plants, the first thing is you need to have the first concrete date. That's the symbol of the start of nuclear power plants. Basically, you pour the concrete into your reactor size, and that's show people you start building these nuclear power plants. And next, you do a lot of constructions, like all the reactor buildings, a lot of infrastructure. And when you finish the work, you start to install the dome. I always think that's a really fancy process. You lift up the dome and position it exactly on the reactor building. And after that, you finish all your structural construction and you start to install equipment. There are a lot of equipment like nuclear reactors, like the steam system, ventilation system, and you install all this equipment into the nuclear power plants. And next stage is the testing and commissioning stage. And you start with the cold test and also the hot test, and also you loaded the fuel and test the nuclear reaction. And after that, you do the commercial operation. So basically, that's how you build a nuclear power plants. And it's in most of Chinese nuclear power plants, they follow the 3 stages: the structural construction stage, the equipment installation stage, and testing and commission stage. And usually they have different firms to do this work. For construction, you will have the construction firm to do the structural construction. For the equipment installation, you will have the installation firm. And for the testing and commission stuff, usually that's conducted by the owners of the nuclear power plants. So our thinking is like, if you have learning, and for those construction firm or installation firm, they probably have cumulative experience, so they can build nuclear power plants faster. That's a hypothesis. And let me show people the data here. I think it's not really readable, but basically the figure showing here is the horizontal axis, that's the time. And the y-axis, that's all the Chinese nuclear power plants ordered by their construction started date. And that's the first one nuclear power plants to the most recent nuclear power plants in China. And the color you can see, that's their construction duration. The yellow ones is their structural construction period, and the blue ones is their installation period. And finally, that's the testing and commission period. And basically, we use some regression model to understand, is there any learning on the construction time? For these construction firms, for these installation firms, when they have more experience, can they build that faster? Our the results basically showing the learning effect is very limited in reduce the construction time of nuclear power. But there are 2 things I think very interesting, and they are statistically significant. It's like we find the firm-specific positive learning in the structural construction period, and the negative learning, firm-specific negative learning in the installation equipment period. I think it's not surprising, right? Like the structural construction period, that's a relatively standardization process. For every nuclear power plant, you do the same thing. So something you can learn. But for the equipment installation, like different models, different nuclear power plants, their equipment are very different. So it's really hard to learn. And also, it's become more and more complicated over time. So in the regression, that's like a negative learning. That's a second channel. The third channel of learning is like, we know that most of the Chinese nuclear power plants are built in twin. So you build 2 nuclear power plants simultaneously. Our hypothesis is like if you have learning, probably you have more experience from the first units. You can reduce the construction time for your second units. But you can see here, the figure is showing the construction time for the first units and the second units. And statistically, there is no significance. I think this is also not surprising because the first unit's effect, we actually also observed that first unit's effect I think in the United States. It's basically for nuclear power plants construction. You really want to build the first units as soon as possible. So you can get revenue, you can catch the government deadlines, and you can attract media attention. So I think the learning is pretty limited to offset this first unit effect. So there's basically no significance here. So basically my argument is trying to say learning is very limited. A lot of people saying like if you can have cumulative experience, you can make the advanced nuclear power plants cheaper. Historically, we haven't observed any evidence for that in United States, in France, and also in China. That's a second mechanism. The third mechanism is change in the construction time. What I'm showing here is all the construction times of all nuclear power plants globally from 1960s. And basically, you can say the construction time for nuclear power plants in the United States was nearly doubled since from 1960s to 1990s, and also doubled in France. But in East Asian countries, in Japan, in China, in South Korea, the construction time relatively short and relatively stable. So still in China, this is not a key factor. And one more figure on the construction time. This one, the horizontal exercise, all the nuclear power units ordered by their commercial operation and date. So that's the first units, that's the most recent units. And the rectangle here, that's their expected construction time. And the circle, that's their actual the construction time. And you can say over time, the construction time in China is still relatively stable. And you say only for the first of the kind units, you have the really long construction time. Like the first units for the CNP model, first units for the EPR and AP1000, they take longer time to build. So I hope I persuade people it's like the Chinese construction cost was decreasing over time. And this decreasing was largely driven by the supply chain build out and labor cost. It's an indigenization process. A lot of conventional mechanism we can use for solar wind battery doesn't really apply here. And finally, I want to answer some frequently asked questions. The first question is the export of Chinese nuclear power. Like, can China export cheap nuclear power plants to other countries? My idea is like basically the cost trend we observed in China is really an innovation problem. It's an innovation system and policy problem. So what happened in China does not really apply to other countries. One example is like the only country China has export nuclear power technology is Pakistan. And the data is showing like if you build the HPR model in China, it's about $2 per watt. But if you build the same thing in Pakistan, you double your cost. So this is really like the innovation and policy problem. And currently, the Russian technology still dominates the international nuclear export market. The second thing is like, it's not surprising. The Chinese nuclear is cheaper, right? Everything in China is cheap. Like Chinese solar is cheap, Chinese wind is cheap, Chinese energy storage is cheap. And for China, the real question is like, can cheap Chinese nuclear power compete with cheap Chinese renewables and storage? The IEA has an estimate is like the Chinese nuclear power must to reach $2 per watt to compete with renewables and storage. And I would say based on my data, is currently the nuclear power is roughly in that range, from 1.8 to $2.5 dollars per watt. And the third one is like, is this a unique story to China? Is this a Chinese story? I'm actually not sure. What I'm showing here, people here, is like, I think probably South Korea also have the similar experience. And this is from a previous literature, but I cannot read Korean, so I cannot really validate the data. But I really think what happened in South Korea will be very similar in China. It's like you first introduce technology from the United States, from France, and start building your domestic model and get cheaper and cheaper. And that thing is probably in common with South Korea and China. The Japanese story is very different, but I would say because of the limit of the data, it's really hard to, I think it's really important to understand what's the difference in South Korea, China, and Japan, because they all have the centralized supportive policy for a long time, but their performance are a little bit different. But anyway, this is really like suggestive evidence. I do not have enough data to say that. So finally, let me conclude this presentation. The key question here is like, what's the nature of this cost escalation curves? I think people can already feel that this is a mixed or a combination effect of the nature of technology and the system policy problem. On one hand, nuclear power is a very special technology. It's large scale, it's lumpy, it's risky, and you need to put a lot of money on the capital investment. And it's also a strategic technology. By strategic technology, I mean, in many times, the company want to make it more innovative to show that it's their achievement. And in this case, they actually make it more expensive. That's the characteristics of this technology. But on the other hand, we also see difference in the innovation system, like in France, in South Korea, in China, that's a centralized regime, and in the United States, that's a fragmented regime, and different supply chains. And from policy perspective, we also see different regulations and different financing policy, different regulations. So the final takeaways, basically, what we observe is like historically, we observe the cost escalation curves, especially in the United States. United States is really special. The cost increased dramatically. And also, this is more like a global phenomenon. But here, I want to show people we do have some different example, like China, like South Korea. This shows like the cost escalation curves of nuclear power is really like a mix of the technology limitation and the policy or system failures. And one thing I want to emphasize again is like a lot of things work for solar, wind, or batteries, doesn't work for nuclear power, especially the learning process. You know, a lot of people will say if you have cumulative experience, you can make nuclear power cheaper or build it faster. We didn't see any experience, any historical evidence for that. And even in China, you have the supportive policy, supportive regime. We didn't see any learning in nuclear power. This really likes the inherent nature of the nuclear power technology. And the Chinese approach to break the cost escalation curves is basically supply chain build-up. You do indigenization, you build the domestic supply chain, make it cheaper, do some standardization with stable and supportive policies. But people may ask, like, is there any other approach to break the cost escalation curves? Because usually, like, Chinese approach may not really work in other countries. One thing people are discussing today, I think also another debateful issue, is like, can we redesign the nuclear power technology to break the cost escalation curves? Like if we use a small SMR, the small module reactor is smaller and maybe safer, and you can do the factory learning. That's an open question. I have no answer, but maybe when we have more understanding on what's the really driving forces for the nuclear power, we can have more clear idea. And with that, I'm happy to answer any questions.
Thank you very much. I'm going to take the prerogative of, as the moderator, to ask you the first one. This is a great overview, but I'm still a little puzzled about a couple of things. The first is that if you go back 10 years, China was very optimistic about how many nuclear plants they were going to build. And about every 5 years, that number kept being reduced. Right now, if you look at the present projections, by 2040, China has about 8% of their power would be nuclear, which is significantly less than the 20% we had in the United States a few years ago. I think it's a little less now. The other thing that I was puzzled, so why has there been this sort of decrease in enthusiasm that nuclear was going to solve the electric problem for China? And the second part of this question is you talk about how it's double the price to build the Chinese nuclear plants in Pakistan. I noticed that South Korea just built 4 nuclear plants in the UAE for about the same price they built them in Korea. So why is it so much more expensive for China to export as compared to South Korea to export? But I'm very interested in both answers to both of these.
Thank you for the questions. The first one is like the ambitions in nuclear power build out. I feel the first thing is like you need to understand who sets the goal. Sometimes if you read the reports from the nuclear power industry, it's really ambitious. But other time you read the other reports from like renewable community or other electricity community, that's different goals. And for the government goal, there's only one goal is like set in 2005. That's really ambitious. And other, because of the Fukushima, China stopped that, actually lowered that government goal. But my feeling is like over time, the Chinese usually will say the nuclear power, they want to account for the total electricity from 5 to 15%. That's usually their goal over time. And I think it's relatively consistent over time. Like no one talk about like 50% or 60% in China. That's the nuclear power plants. For the Pakistan versus South Korea, one thing I don't have any data, but I think one thing is like HPR model, the China built is a relatively new model. And China only built that, only commissioned the HPR model. I think that's last, like in 2000, it's 2023. So that's a new model. So you do a lot of testing here, but the South Korean technology is probably more mature. But definitely that's all suggestive, and the cost data is really challenging here to get the answer.
All right, I'm opening it up. Work my way back.
All right, thanks. Great talk. Question. Let me push you a little bit on the notion of a declining trend in China. First of all, have they pretty much finished indigenization so that there's not much further they could go with that? And secondly, it looks to me from that graph, except maybe for 2 dots of the HPR, that in general in China, like in the rest of the world, the 3rd generation is actually more expensive than the 2nd generation. And I'm not sure this is on your chart yet, but my understanding is the pebble bed reactors they were building, which are arguably 4th generation, turned out to be way more expensive than they were expecting them to be. So if you could comment on whether the 3rd and 4th generation is headed back up in China as well, that would be of interest.
Thanks. The first question is the indigenization process. I totally agree. It's like once you reach the domestic content rate, like 75 to 85%, the cost will remain stable in China. That's what happened. So I think that's what will happen. After the indigenization process, the cost will be stable. That's the conclusion here. for the third generation, one thing is like I'm not really sure about this data because this data is like based on their current estimates. So they may have cost overruns likely. So they may be much higher than here. Another thing is I use expected future price data to do the pricing step to adjust it to 2020 price. So a lot of uncertainties here. But I think you are right. It's like potentially the third generation technology will be much higher than the second one. And one thing is like if learning doesn't work, maybe that's it. Will be the final cause of the third generation. But one thing is like the cost escalation curve from the second generation to the third generation is relatively marginal. So nuclear power is still competitive for the renewables like wind, solar stuff. For the fourth generation, what I'm showing here is only the commercially operating units. So I didn't do any demonstration part. For the Chinese faster reactor, that one is really expensive, right? Really expensive, and no one knows. Yeah. And also the Chinese small module reactors also pretty expensive. I think the recent estimate is, I think it's more than $4 or $5 per watt. But that's the initial budget, and definitely they will do some overruns, I guess. So it will be expensive, but the things like that's the first kind of units. It will be interesting to say what the second units they can do. But still, data is so limited and not public available. Yeah.
Thank you. Sebastian Brixey-Williams from the project on managing the atom. 2 questions. Oh, sorry. Knocked over my coffee. First one was, one of the stories that gets told in the West is that Chinese, the regulations around safety and security around Chinese reactors are looser than they are in the West. And I'm not taking a position on that. I'm asking the question of, is that true, and is that a factor in the cost dimension at all? Because that's what's typically kind of pointed at to say this is why they're able to roll them out so quickly. And then my other question was, you've just touched on SMRs a little bit. If indigenization is the sort of defining factor here, what is it about SMRs that's meaning that they're currently looking so expensive, and are they going to be as competitive internationally on that basis, or are they going to run into trouble for other reasons? Thank you.
Oh, sorry, what's the first question again? Well, the safety, right?
Security.
Safety, right? Yeah. So first, I'm not an expert on the nuclear power safety, but what I learned from the Chinese news story is more like when you replace the foreigner equipment with Chinese equipment, they try to hold the safety standard, but to use the Chinese supply chain to build that. But maybe, and another thing is like after Fukushima, because all these nuclear power plants, they are constructed during Fukushima, they also do some safety improvement on that. And if learning do exist, maybe that safety regulation offsets that learning here. That's one hypothesis. What I'm actually trying to collect all the safety measures for each nuclear power plant and try to understand if they really impact learning. But anyway, I do not have enough data to say anything about safety here. And the second is about SMR. I would say like one based on my data, I found like still Chinese SMR is cheaper than SMR in the United States. That's the Chinese supply chain stuff. But can they be cheaper? Because they are already indigenized. So if they can be cheaper, that's a problem. So and I don't have an answer on that. Yeah.
Thank you. Just a question going back to construction. In terms of risk ownership during the construction process, US, it seems like a lot of the problems are driving from company, Westinghouse, runs into a problem, cost overruns, and then they run out of money, go bankrupt. How is that different in China? Is there more government kind of stepping in and owning the risk so that the company doesn't own all of it during the construction process, or is something else going on?
I think if you build a nuclear power plants for 50 years, for 10 years or 15 years, that's probably a really big concern. But relatively, I think what I'm showing here is like the construction time in China is relatively short, within a reasonable range. So if you think about their capital cost, and the first is that the construction time is relatively low, and their interest rate is because they are state-owned company and they receive really low interest rate. So basically, that's not a huge problem here. But you can definitely debate whether this is because the system or the private versus state-owned company, or what really contribute to that difference. People will argue for nuclear power. I think the first important thing is actually not construction cost, it's their interest rate today, right? They get really high interest rate. I mean, United States and France. So how to lower the interest rate is basically the first question when you think about building new nuclear power plants. And I think that's a system stuff and policy stuff, right? Rather than technology itself.
I will ask you a couple of more questions. The first is, I noticed that most all of the Chinese nuclear plants are built on the coast. That they have not built, as far as I know, anyone inland. And so water seems to be a big concern. I mean, in the United States, we have nuclear power plants all over the place. And so I was wondering, what has been the impediment to moving nuclear power off of the coastline? And my second question is, you talk about the interest rates that these facilities are able to get. If I am a manufacturer of the supplies that go into a nuclear plant, am I also a state-owned enterprise primarily, or most of the supply chain in China owned by the state as well as the actual construction of the facility?
The second question, that's basically true. Most of the companies along the supply chain that's state-owned company. And the second question is like, before Fukushima, there are actually a lot of nuclear power plants in the pipeline and in the inland area. And people don't do that is after Fukushima, if you have the safe water, it's safer. And one thing is really interesting is like, I think currently the Chinese nuclear power industry, they are thinking to build nuclear power plants inland. The evidence is like, you can see most of the nuclear power plants today, they are in the coastal area and they use the seawater cooling. But if you want to move that into inland, you need to use a cooling tower to do that cooling system. And the most recent Chinese nuclear power plants are using the water cooling technology rather than use the seawater cooling. And I think that's this one slide, or this one, the typing link, I guess. And that's a symbol. They actually want to test this technology and to build that inland. But basically, that's still not in my backyard. The safety concern over here after Fukushima. Yeah.
They had several inland sites approved. They had several inland sites approved prior to Fukushima, and then they have not allowed any of the construction on any of the inland sites since Fukushima. But they could decide to do that at some point in the future. In the longer term, there are advanced designs that wouldn't require even a cooling tower, that use different approaches to cooling than water.
Any more questions? If not, let me thank Shangwei for a terrific presentation, and to tell you that we will not be having a seminar next week since you guys are all on spring break. And we will reconvene on the 24th of March, where Shangwei Liu, who is a professor at the business school, will talk about AI and the electric grid. So thank you very much, and we'll see you in 2 weeks.